or 1 per unit means something to you, okay? But you could pick the square root of 43 pi for a base if you wanted to. But that makes no sense. That doesn't, we don't relate to that. You know, I like to sit and, you know, if I'm thinking, well, let's see, I want to talk about the voltage of that outlet right there. Well, we all know that that ought to be somewhere around 120 volts. If I sit down here and I ponder that voltage, and I want to talk about it in percent, well, if it's a little bit low, maybe 114 volts, okay? I still run my computer. Well, 114 volts is 95% of something, but 95% of what? 120, okay? But if I told you, well, the voltage is 95%, you'd say, well, that's probably okay. If I told you the voltage is 98% of whatever it was supposed to be, you'd say, well, that'd probably be okay. You go ahead and plug your computer in and you can go on and be happy. Okay? So it makes sense to pick a voltage base for an application that means something. Okay? Something we can relate to. If we're talking about an outlet, you know, okay. Pick a voltage of 120. You don't have to do that. Okay? We could pick a voltage base of 240. And then if I wanted to talk about the voltage of that outlet in percent, what would it be? 50. So I'm going to call Mama and say, Mama, voltage of my outlet is 50%. She goes, that's too low. Okay? Because 50% sounds low, but 50% of what? Okay? So pick the bases wisely. Now, what we tend to do is we tend to try to pick the bases so that, like I said, from a, let's say, a visualization perspective, so that 100% means something. Okay? That's kind of the practical side. Well, now, if you go back to the days before we had calculators, and I can barely remember doing this a long time ago. Back when we used to have to calculate things with slide rules, okay, a slide rule is kind of like a mechanical calculator. You probably never even seen one. And, okay, don't worry, you hadn't missed anything. But nonetheless, because it was a mechanical calculator, it tended to calculate things over ranges of tens, okay? It's physical. You move it around, okay, to do calculations. If you wanted to calculate over, let's say, 2 ranges of 10 or 2 powers, like if you wanted to do calculations involving numbers from 1 to 10 and 10 to 100, you could get by with a physically small one. If you wanted to do calculations over 3 ranges of 10, a little bigger, 4, 5, you get the idea? Okay, so in those days, it was, you might say it was essential for us to choose bases so that all of our numbers would kind of get in the range somewhere around 1. That way we wouldn't have to have a slide rule that was as long as across this room, try to move stuff around. All right. So, there's a couple of reasons to choose bases wisely. All right. We like to choose them so that our numbers go to 1 to 1. I'm sorry. We like to choose them so that our numbers kind of gravitate towards 1. From a practical reason historically, and from a visualization reason even to this day. Okay, so we pick here, we pin the tail on the donkey, so to speak, over on at the load node. All right, we picked those 2, we calculated the other 2 that we normally need. Now what? Well, we're not done. We got more of the circuit. So there is a relationship associated with the ideal transformer. We pick that one, and we can calculate the voltage base at another node using that relationship. All right? We pick that base for power over on the other side, on the load node side. But again, we used a relationship with the ideal transformer to calculate that S base. It looks like we just wrote it down, but you could say we calculated it because for an ideal transformer, the power in and power out are the same. Okay? All right, well, once we have new voltage and power bases, then we calculate the others that we need. Now that we got all those bases done, we can convert circuit over into per unit by just dividing everything by the proper base. Now, one thing I want to talk about here a minute. Okay? Look at this. This is a complex number. Okay? It's a voltage, it's a complex number. It's on this side, so we gotta use the bases on this side. So I'm gonna divide this by something. What am I gonna divide it by? Well, I'm gonna divide it by that base. Notice that I'm dividing a complex number by a scalar. Bases are always scalars. Okay? Now here comes a funny story, but I hope you never forget this. And I don't know whether it's because of the funny story or whether you're all just real smart, but seldom do you make this faux pas. We've talked about going to the shop and buying some pants. Go into the shop and it says it's 50% off. You know, oh man, what a sale. So I'm gonna buy these pants, I'm gonna go up to the register. My daughter used to work at the recycle, that's what I call them, recycle shop over in Opelika called Fringe. You know, it's some kind of consignment store. But anyway, and they would always have these sales. Well, my daughter's pretty smart, but not everybody that works behind the register is that smart. So I'm gonna go up to the register one of these days and I'm gonna say, it says it's 50% off. 50% off of what? The original price, you know, $50. No person working behind the register. It's not 50, it's not 50, not that. It's 50 at an angle of 43. That makes sense? That makes no sense. Are you gonna talk about a percentage of a complex number? Explain that to your mother or the person working behind the cash register. That makes no sense. Basis, remember, all base is the of what? We talk about a percent of what? Whatever the base is. You know, do you want to, yeah, I'd love it if Alabama Power sent me a bill and said, oh, my bill's 50% less. Great. My bill is 0 plus J something. The imaginary part. That makes no sense. Bases can never be complex. Never. Okay, that has no practical meaning whatsoever. So don't ever do that. Look at them all. Okay, every one of them are scalars. They always will be. None of those variables have bars on them. Okay, they're all magnitudes or scalars, you could say. Okay, bases are always real numbers. They're not the real part of a complex number. They're not the imaginary part of a complex number. They're certainly not a complex number. They are a magnitude. Okay? So, no. Don't go to the sales counter and say, I want 50% off of 1 plus J3. People look at you funny if you do that. Okay? Don't do that. And if you do that, don't tell them you know me and don't tell them I told you about it. So, remember, bases are always magnitudes. All right, so you see that show up here. If I divide 12,470, which was the SI unit voltage, if I divide that by 12,470, which was the base, I get 1. Notice that putting it in per unit does not change any of the angles. If you divide a complex number by a scalar, it doesn't change the angle. That right there ought to be minus 25 because the unit on a per unit quantity. Don't do that. Typo alert. Okay? Get rid of that D. Okay, so got that voltage in per unit. There's the impedance. How did I get that? Well, if you go back to the SI unit value and divide it by the base impedance, that's what you're going to get. Notice that, let's see, it looks like the reactance is 10 times larger than the resistance in per unit. It looks to me like the reactance is 10 times bigger than the resistance in SI units. Dividing a complex number by a scalar doesn't change any of the angles, okay? Not one bit. So, 4 equations, 4 unknowns. Look, what's wrong? No, go this way. Or 1 equation, and depending on what we're looking for, 1 equation stop for one. Okay? Now, we gotta be fair to ourselves. 4 equations and 4 unknowns, or 1 equation and 1 unknown plus that. Okay? Can't overlook that. So for a little problem like this, this little guy, it's probably about a toss-up in terms of the effort required. I don't know. I never really looked to see, how many calculations I have to do. Okay? But I'm not going to stand up here and tell you that, oh, that's all there is to it. Okay? We're not comparing this with that. Okay? It's this guy compared to all of this setup work and that, and we're still not quite done, because I still, once I solve that simple circuit, I still have to convert per unit answers back to SI answers. Okay? So, why do we do that? It looks like maybe even I'm doing more work here than I would have if I just solved 4 equations and 4 unknowns for this little problem, maybe. All right? But I told you about this last time in, kind of setting this up. But one thing you have to realize is that very seldom in power engineering applications do we start with the problem in SIU. Most of the time, for 2 reasons, and I'll remind you if I didn't tell you last time, I'll tell you in a minute. For 2 reasons, we typically start already in per unit, okay? One reason that's true is because somebody did whatever job you're gonna get when you go out of this door, somebody did that job before you got hired. Somebody already converted almost everything into per unit. You don't have to start from scratch. Right? Now, if you go to work in a consulting company and you're gonna go analyze some power system in a chicken feed mill, no engineer's ever been in there before, yeah, you might have to start that from scratch. But in general, in power engineering applications, we don't have to start from scratch. All right? So you don't have to go through that setup mess about choosing bases and all that. Somebody had already done that. All right? The other reason that you usually don't have to do that setup stuff is because oftentimes the manufacturer of equipment will give us the information about the equipment already in per unit. Okay? So we don't have to do it there either. Now let's take a look at that. How that works. The easiest thing to visualize at this point in our progression is a transformer. Okay? Now this is a nameplate picture of a transformer. This is a pole mount, what is it, 15 kVA? Yes. This is a pole mount transformer. The thing would be on the pole outside your house. Manufactured by Howard Industries. If you never heard of Howard Industries, they are a, you might say, a transformer manufacturer based in Laurel, Mississippi, and they make a lot of transformers. Okay, if you spend much time on the interstate in the southeast, you'll see flatbed 18-wheelers rolling back and forth, loaded down with transformers. They're probably coming from the plant in Laurel. Okay? All right, well now, what we got on here? Well, we got all kinds of good information. Now, one of the things I can point out to you is, for example, we talked about how when transformers are wound, how they're wound, and some of the notation that's used. Remember I told you about H's? H's are for the high voltage winding, and X's are for the low voltage winding, okay? I also told you that transformer like that serves your house, it has 1 high voltage winding, it has 2 low voltage windings. Each of these would be 120 volts, and so when you tie them together like that, then here you got 240. Okay, so this is what we were talking about in some of those other pictures. So what all else we got up here? Well, here's the power rating, okay? Here's the voltage information. All right, let's see what all else we got in here. Well, we got a serial number. That's enough for us. Frequency, temperature. Oh, look, it says read instructions before operating. That's pretty good. Oh, how much it weighs, stuff like that. But that's not why we got this slide up here. The reason we got this slide up here is because of that. percent imp. Now, what is an imp? Are we talking about a dwarf here? No, I don't think so. Imp is an impedance. Okay? Percent impedance, 2.4. The manufacturer, in this case Howard Industries, is telling us the impedance of that transformer in percent. They've already picked bases and done all that stuff. They're telling us the number. Okay? Now, percent. Here we go again. Let's go back to the shop. Go back, talk about 50% off pair of pants. 50% of what? 2.4% of what? Okay? I mean, I took that picture of that transformer when it was sitting on the back of a flatbed truck. I don't remember where. Let's say on the side of the road. Okay? But I know 2.4% of what? I know exactly what they did. And you're about to know what they did. Okay? When a manufacturer, in this case Howard Industries, when they give us percentage information, the of what is always the ratings of the piece of equipment. Always. Okay? Remember I told you that in power applications, we pick two bases. And what two do we pick? We pick a voltage and a power. The manufacturer picked the voltage and the power. Alright? How do we know what numbers they picked? They're right there on that nameplate. Okay? They're right there. Now, in this case, for this particular kind of transformer, you have to understand what this, you might say what this notation is, okay? Because you got two voltages on the high side and you got two on the low side. All right, so how do you interpret that? Okay, the reason that you got to is if you use this transformer in a three-phase application and you connect up this in delta, then it's gonna be this voltage. If you connect this up in Y, so this is say a phase and a ground, it's gonna be that voltage. So that's why you got these different numbers. But for this case, the manufacturer chose 7,200 volts on the high voltage side and 15 kVA. The turns ratio is 7,200 to 240. All right? Now, if you want to recognize the individual windings on the low side, the two 120 volt windings, well, those turns ratios would be 7,200 to 120. Okay? So, 2.4% of what? Well, there's the power, there's the voltage. Okay? Just 1 minute. There's the power, there's the voltage. Okay, I'm just pointing to this side. Ignore the fact that this is low voltage. Okay? There's the power, there's the voltage. Now that percent imp, that's an impedance. I need that. Okay. Once I've got these two, I can calculate that. I gotta, make a step or two, but I think I can handle that with a phone calculator. Okay? Sorry.
So you have to know whether it's connected in wire delta before you pick your voltage base.
And careful with that. Kinda yes and kinda no. Applications where you make field connections, where you make three-phase field connections with individual transformers, they can be a little bit tricky. And in those applications, the answer to your question is yes. Okay? If you have a three-phase piece of equipment, the answer to your question is no. All right, we'll talk more about that, I don't know if we'll get to it today or the next day. Okay? That can be a little bit tricky. And we're not gonna spend a whole lot of time talking about it, because there's quite a few variations on that. All right. So, manufacturer kind of saves us. But, transformer, okay, right here. Well, here's an impedance and a source and load. So now let's say that this transformer is that Howard Industries transformer. We got the nameplate. The manufacturer is telling us the percent impedance, right? But what did the nameplate say? It said percent impedance 2.4. Look at that circuit. You know, and pretend instead of 30.9 or 309.5, ignore those numbers. Pretend that it was 2.4 somewhere. Wait a minute. 2.4. Is that R? Is it X? Well, 2.4 is certainly not a complex number, is it? I don't know. So in that circuit right there, I see an impedance. It says 30.9 plus J309. But on that nameplate, it just has a number. If I'm gonna calculate something in that circuit, I need an impedance. I need an R and an X. Okay? That ain't on the nameplate. It never is on the nameplate. What do we do about that? Well, you got about 3 choices of what to do about that. Okay? One thing you can do is you can call the manufacturer and ask them. Now, if you do that, if you get somebody knowledgeable, they can give you a reasonable estimate of what we call the X to R ratio. And we'll deal with that in a minute. Okay? From that piece of information, you can calculate the complex impedance, and I'll show you how in a minute. Okay? So you can get the missing information from the manufacturer. All right. Well, you guys probably, if you haven't already, you soon will. You'll deal with either calling or emailing or somehow contacting some manufacturer or some vendor for information about their product. Now, are you always 100% confident when you contact a vendor that the information you get back is what you need? Do you trust it? Okay. There's no telling how many times that I have contacted vendors, either on the phone or chat or, email or whatever. And I get back some piece of nonsense. I'm like, nah, there's no way. All right. So you're making kind of an assumption that, oh yeah, I'll call up the manufacturer, just ask them. Well, assuming you get somebody on the phone that knows what they're talking about. By the time you get through playing, 10 levels of phone tree. I hate phone trees. So it's an option, but ain't not good. Another thing you can do is you can look at what's called the transformer test report. Okay? Every transformer that's manufactured has to conform with a variety of performance and safety standards. Part of that conformance testing results in the manufacturer being able to determine the complex impedance. Okay? Now, if they have it, they'll give it to you. But for little transformers like that, Howard Industries rolls thousands of them off the end of the production line every day. Okay? Lots and lots and lots of them. They don't test every one of them. They might test 1 out of 100. Okay? I don't know what percentage of them they test, but they certainly don't test them all. Well, just because something's made on a production line, is everyone going to be identical? If you and I both go up to the Kia plant up there in LaGrange and we pick out 2 cars that came off the same assembly line, they're parked right next to one another, and we get them and drive them, you might get a great car, I might get a lemon, right? How could that be? They came off the same production line. They got to be exactly the same. Of course, that's foolish, right? There are going to be variations. So if mine didn't get tested and yours did, you might know what your transformer is, your information, but I wouldn't. Okay? Now, knowing what yours is a whole lot better than nothing. okay? And we call that knowing typical information, okay? And a manufacturer can tell you what that is. Utility companies have big databases full of typical information. A big company like Alabama Power, Georgia Power, that buys hundreds or thousands of these things, well, when those acquisitions, those purchase acquisitions, when they're sent to the vendor, in this case Howard Industries, when those purchase orders are sent out, in the purchase order, okay, will be something where Howard Industries has to give typical impedance information. Not impedance information for any specific one, but typical. And, utility companies save that, okay? So we might have historical information. All right. Now, if it's a big transformer and you spend a bunch of money on it, the manufacturer's gonna test it. And you'll get the test report when you buy it. Okay? Not for those little things. But to kind of put it in perspective, again, that picture I showed you was, that little transformer was sitting on a flatbed with 50 of his buddies going I don't know where. Okay? No, they didn't test that. The ones that you might see rolling down the interstate, with wide load vehicles and in tows and ahead of them and behind them and a bunch of flashing yellow lights, and red flags out on the sides, okay? If you see one of those, yeah, that one was tested. And if you bought it, you can get it testable. Manufacturer did it, they had it, and they'll give it to you. And it has all of the information. So that's a place, if you spend a bunch of money, you're gonna get the specific information. It's not gonna be on the nameplate, it'll be on a piece of paper. Well, experience, after you've done this a while, you can begin to develop a feel for about what the relationship between that percent number is and the R and the X. Okay? And so with experience, you kind of learn what to assume. There's some information, you might say, that's published, whether it's, online or in old books or whatever, it doesn't matter where it's published, but there's some information, not too much though, really, at least not that I found. And you can call up somebody else and ask them. You call me up and say, oh, I got this, what should I do? Okay? But the point of all this is, the information you need is not on the name. Okay? You gotta do something. Now, what we typically talk about is what's called an X to R ratio. Okay? Now, it's as simple, that thing, that X to R ratio, it is as simple as the name suggests. There's X, there's R. The X to R ratio in this case is 10. 309 divided by 30.9 is 10. So X to R ratio, 10. Okay? 10, 2, 20, whatever the number is. Okay? So what's on the nameplate now is the magnitude of that complex impedance. We have to use that X to R ratio and the magnitude together to get that complex impedance. And let's see how we do that let's just work through the example and see. All right, so let's take this little guy. Okay, so 7200 to 240, 25 kVA transformer. On the nameplate it says percent imp is 3. And let's assume the X to R ratio of 2. So, what we got here? Now, the way this works is, can you see that? Probably not. I'll be back in a minute. Let me go to the office. Well, you got a couple? Thanks.
What are you doing with all those pins? That's where you're a pin thief. All right, so let's try this. Oh, look at that. Beautiful. All right, so the idea here is based on this notation, okay?
The general notation that we use for impedance, Z, notice it's got a bar, complex, is R plus JX. Now, if I want to talk about the magnitude of that impedance, we know how to find the magnitude of a complex number. Square root of R squared plus A squared. Now, this that's the percent imp. Okay? The X to R ratio in this case is 2. The percent imp is 3. So now, look at this. Here I got one equation, get rid of that Z and replace that with a 3, okay? So I got one equation right here and 2 unknowns. The 2 unknowns are R and X. Here I've got one equation and 2 unknowns. The 2 unknowns are R and X. So I got, between these two, I've got 2 equations, 2 unknowns. Okay? Now, you learned a long time ago in math class, 2 equations, 2 unknowns, take a day off. I can solve it. Okay? Well, yes, but those are nonlinear equations. They're kind of yucky. So how do we go about doing it? Well, we're going to deal with this with substitution. Now, you can do this different ways, and different people do it differently. Okay? But what I do is I will plug in the X to R ratio. Okay? I'll substitute that in for X. Okay? So, if you look at this little fella, we could say that X is equal to 2R, right? Now I'm gonna substitute that in right there. So, I'm gonna have 3 is equal to the square root of R squared plus 2R squared. Or 3 is equal to R, because obviously I'm gonna have R squared here. That's the square root of 1 plus 4, or R square root of 5. Okay? And then so R will be equal to whatever that is. I do this so many times that I don't ever actually write that down. I always do it the same way. So I get this off the nameplate, and I get that somewhere, either from experience or wherever. Get that off the nameplate, I got this, and I just plug it in right there. I'm gonna put that 2 right there. Okay? So I'm always, in my mind, I'm always saying that the percent imp, whatever that is equal to R times the square root of 1 plus whatever that X to R ratio is squared. That's what's in my brain every time. Now, I would encourage you, at this point in your learning career, I would encourage you not to jump straight to that end result, okay? Make sure, how long does it take? 30 seconds to go through those little steps? Learn the little steps. After you've done it a billion times, then all right. Then shortcuts are okay. But the ancient wisdom applies. Shortcuts make for long delays. Be careful with them. All right? So, in this case, now, I don't know what the number is. Anybody got a calculator? You got pens? I know how to calculate it.
1.34? All right, 1.34 what?
Okay.
Hmm?
Do you want more numbers?
No, 1.34, well, now I want a unit. 1.34%, right? We're still in percent. So, might be helpful to write that now, 1.34%. Okay, well, how do I get X? Well, X is nothing more than what was it, 2? X is 2 times R. So X is gonna be, I can even do this in my head, 2.68%. So, if I want now to talk about Z complex, and it says do it in per unit, that's gonna be 0.0134 plus J 0.0268. Shazam, done. If we wanna draw the equivalent circuit in per unit, well now remember, in per unit, the ideal transformer is gone, so the equivalent circuit is just gonna look like this. And of course, there's the impedance. So, if I was working a problem like this one, there's the impedance. I can hook the source up, load up, and proceed to calculate. Okay? Now, the equivalent circuit in SI units with the impedance on the high voltage side. And then do it again, put the impedance on the low voltage side. Now, what's this about? Okay? Now, at this point, this impedance is in per unit. Okay? Now, that ideal transformer, which has a ratio of 1:1, it could be here or it could be there. Okay? Could be on either side. If I put the ideal transformer here, normally, my picture doesn't show it. But it's kind of customary when we draw an equivalent circuit for a transformer, it's kind of customary to put the high voltage side on the left and the low voltage side on the right. Source on the left, load on the right. You don't have to do that, but that's kind of how people think. I guess it's because in English, we tend to read left to right. All right, so if we think like that, and again, we don't have to, but if we think like this, if the ideal transformer is here, then that impedance is on the low voltage side. Okay? If the ideal transformer is here, then that impedance is on the high voltage side. But now hold on a minute. In reality, this is a transformer, right? Yeah, of course it is. A transformer, what does a transformer consist of? Well, let's see. We've seen this little picture before. Transformer's got 2 windings, right? Each one of those windings has got some impedance. This right here represents the ideal transformer, and these are its impedances. So how is it we have 1? Well, in per unit, when this goes to a straight line, I got some impedance over here, and I got some impedance over there, right? And they're in series. I just add them up, and I get 1, like we drew over there. So really, the ideal transformer sits right here, okay? But because this is in series and we add them up, manufacturer only gives us 1% M, not 2. Because I add them up, I gotta decide, do I wanna put the ideal transformer on the left or the right? And that's our issue here. So, let's suppose, which one did it say first? Impedance on the high voltage side, over this one. So what I wanna do, let's call this Z, H, V, S, I. Okay? I wanna find that. Now, that's 7,200 to 240. Yeah. All right? So I need that. Well, how do I go from per unit to SI? I need the base, right? Okay. Well, do I choose the base? Can I pick it? Well, that's what we said, right? Pin the tail on the donkey and pick it. Or pick two, right? Well, but we already have information given to us in per unit. We're trying to get it out of per unit. We need to know what the manufacturer already picked, somebody else picked. And what did they pick? They picked the ratings of the equipment. For the high voltage side, which is where we're working, there's the voltage base and there's the power. So, in this case, we could say that S base is 25 kVA and the voltage base is 7,200 volts. Okay? Now what? Now I need to calculate the current base. So the current base is 25K divided by 7,200. Somebody with a calculator get busy. The impedance base then is 7,200 divided by whatever you're about to tell me.
3.472.
3.472. 3.472, of course, that's in amps. Now what's the impedance base? 7,200 divided by 3.472. Sorry for getting down kind of low. I know it's hard to see the back. What is it?
Is 2.074.
Whoa. No way 7,000 divided by 3.
K. 2.
Okay, what? Give me it in.
2074.
2074, that's it. Oh. Okay? So now what? Now, I can write down that the impedance on the high voltage side of the transformer in SI units is 0.0134 plus J 0.0268, which is a complex number, times 2074. And of course, now that's gonna be back in ohms. Okay? Whatever that, we don't have to write that down and we don't have to multiply that out. Okay, any questions about that? Get rid of that. And get rid of all that. Now, let's do this again, except this time, let's put it on the low voltage side. So what does that mean? Well, that means that the ideal transformer is here. The turns ratio or the rated voltages are still the same, but now the impedance I'm gonna put there. And let's call this ZLV SI. Okay? So how do I do that? Well, I've got the impedance in per unit, I gotta get it out of per unit by multiplying it by the base. So where do I get these bases? Can I pick them? Well, no, they were already picked. The manufacturer picked them, and they picked the ratings of the equipment, okay? The rating of the equipment in terms of power is the same on both sides. The rating in terms of voltage is different, okay? We're working on the low side now, so the base they used was that low side voltage, 240 volts in this case. So S base remains as before, 25 kVA. The voltage base on the low voltage side, 240 volts. The current base, now with this we gotta calculate 25K divided by 240. The impedance base is gonna be 240 divided by what you're gonna tell me in a minute for the current base.
$104.
104 for the current,
Yes, sir.
104 for course, that's amps. So 240 divided by 104 is
2.3.
2.3, of course, that's ohms. So now what? Now I simply take my per unit number, which is 0.0134 plus J 0.0268, and I'm gonna multiply that times 2.3, and that'll come out in ohms, and I'm done. Now, why did we go through this? You know, if the manufacturer gave us the information in per unit to start with, why did we go to the trouble of converting it to SI? If we had this given to us, not quite, remember, we had percent imp, and we've learned now how to use the X-star ratio to get a complex impedance. So, in effect, the manufacturer gave us that. If that's true, why in the world do we want to go to the effort to go back to something like this? Why do I want to, I would never want to do that. Okay? The idea of per unit was to make life easier. And we see that in this little circuit, I got 4 equations, 4 unknowns, whereas once I get it in per unit, I just have 1 equation, right? Much easier to deal with. So why in the world would I go back to this? Well, unfortunately, we talked about this before. Everybody got this, can I erase it? Everybody still writing? Every time I wear this shirt, my mother always says I'm supporting Alabama. Is that true? Mom, quit that. We've drawn this little picture a million times. I think I have the world's most illustrated dog.
It's a woman tell.
I would claim to be an engineering teacher, but you'll have to assess whether I'm that or not. I am not an artist. That I could easily say a lot of things I am not. Okay. You know, that's, I can't get any more simplistic than that picture, okay? And the critical thing here we want to note is that's got 3 transformers, okay? Every one of them, all 3 of them, okay? Each one of these has a nameplate, all right? Each one of these has a percent imp on its nameplate. So that means that percent of what? As far as the transformer on the left, the one connected to the source, that we conventionally refer to as a generator step-up transformer, or GSU, we usually just say. As far as the GSU is concerned, the percent impedance is the percent of the ratings of that transformer, right? Okay. What about this? What about this guy? Okay, this might be what we would refer to as a substation transformer. Percent impedance, percent of what? This is going to be in percent on the ratings of this piece of equipment. Percent of what? The ratings of this piece of equipment. Now, this is a transformer that's on the pole outside my house or yours.
all right? You might say, for discussion purposes, that the average demand of your house and mine is somewhere around 1.5 or 2 kVA, something like that. That's source. Next time you read an article about, some power plant or some power generator, the media likes to talk about power generation in terms of how many houses it can power. Oh, we're gonna put up enough solar panels to power 10,000 houses. I'm not saying the media's dumb, or they are. I didn't say that. They talk to us that way because we can relate to that, right? If I try to explain to my mother how many megawatts a generator produces, she doesn't have a clue. But my mama can visualize, as can yours, it takes a lot more power to power 10,000 houses than it does one. Okay, you can visualize that. So, think about that a minute. That transformer over there feeding the house, that's one house. That's gonna be a relatively small transformer. That GSU has gotta handle all of the power for that generator. And the generator, quite obviously, can power lots and lots and lots of houses. Okay? The power rating of that generator, of that GSU, is much, much, much greater than the power rating of that transformer outside of the house. So now, percent of what? These ratings. Percent of what? These ratings. The issue at hand is these ratings and these ratings are not the same. Okay? And because they're not the same, what that means is this big circuit right here, when I draw this big circuit, I can't use this per unit number and that one in the same circuit because the bases are different. They're not consistent. Okay? And they never will be. So what do? In order to make ideal transformers go away, we have to follow our procedure. Okay? We can pick two bases, one place, and one place only in the circuit. So we could make a little circuit for this, right? But only in one place can I pick two bases. But look what happened. This number is based on the ratings of this. This manufacturer picked right there. This manufacturer picked right there. You can't do that. Okay? Because that would in effect mean I'm picking in two different places. Can't do that. So what do? We pick in one place. We do. Put the manufacturer down. We pick wherever we want to. Pin the tail on the donkey, there. All right, so I'm gonna pick right there. Once I pick there, now I can calculate all my bases. I can calculate current and impedance here. Okay, I can calculate voltage, power, current, impedance there and everywhere. We know how to do that. Yeah, well, we're learning now. Okay, but I did it based on my one pick. Now what? Now that I have, based on my choice and my calculations, now that I have a consistent set of bases everywhere, now I can put everything in per unit. How do you put something in per unit? You have it in SI and you divide it by the base, right? This manufacturer gave us this in per unit on his basis. In order to put it into per unit on my basis, based on my one pick, I gotta get it out of per unit and into SI. Then I'm gonna put it into per unit with my choice. And we run into that regularly in power engineering. Because when manufacturers give us per unit information, they're giving it to us on their basis. We've got to get it into per unit on our basis. Okay? And it's hard to see that when you look at a little problem like this one. Because all we're doing is we're using the manufacturer's basis, okay? Most of the time, our bases are gonna be different from those of the manufacturer, particularly the power base, okay? We will see when we get into bigger circuits, the power base, once we pick it, is the same for the whole problem. Voltage bases vary based on transformers. So, in our little blue circuit over here, I'm gonna pick somewhere. Let's suppose I pick right there, okay? So I'm gonna pick an S base. Once I pick it, at this node in the circuit, it's the same everywhere. But, I'm also gonna pick a voltage base. Those are my two typical choices. Now, the voltage base here is different than the voltage base there, because I got a transformer system. We've seen that. So that means that the impedance base is gonna be different. Well, all right. So I got different impedance bases all over that circuit, not just one like this looks like. You can kind of get the idea, different impedance bases, because we had to use a different impedance base when we put it on the high side or the low side. So dealing with this issue is why we have to do this right here, and we have to do this regularly. Right? Unfortunately, there's no way around that. All right? Okay. So, all that we've talked about has been for what you might call single phase or per phase. What about three phase? Well, now there are a lot of ways you can choose in three phase, but the basic premise remains. I can pick two bases, and two bases only. We customarily pick a power base and a voltage base. The issue is what power, okay? Because in three-phase applications, I can talk about picking the power in one phase, or what we might call the single-phase power, or I could pick the three-phase power. What do you want to pick? Well, you could pick either one. We customarily pick the three-phase power. We don't pick watts, we don't pick volt amperes reactive or bars, we pick volt amperes, period. Apparent power, S3 phase, no bar. That's what we pick. You can pick the square root of 43 pi for that value if you want to, but we've talked about why that's a little bit silly. Pick something reasonable. What about voltage? Well, in three-phase applications, I've got line-to-line voltages, and I've got line-to-neutral voltages. Which one do you want to pick? You could pick either one. Customarily, we pick the line-to-line voltage. So, in three-phase applications, our two picks are line-to-line voltage, three-phase apparent power. Okay? Everybody does that. And nobody says that. In the event that you deviate from that well-entrenched practice, it is your responsibility to draw attention to the fact that you deviate. Okay? You know, you go driving down the road. When you get ready to change lanes on the interstate, you know, most people gonna put their blinker on, right? You're deviating. And you indicate that you are deviating. If you deviate from those picks, then you better be speaking up, all right? So, these are the two that we picked. Now, that doesn't mean that those are all we need, man. We need a bunch of different bases in three-phase applications, okay? I guess you could say these are probably three of the most common ones. A lot of times when we're working problems, we need a line and neutral base. Well, we know there's a relationship between line-to-line voltages and line-to-neutral voltage. Line-to-line is equal to square root of 3 times line-to-neutral. Use it, and we do, to calculate the line-to-neutral voltage base. All right, what about three-phase apparent power? Well, we know that S three-phase is the square root of 3 times the line-to-line voltage times the line current. These are known AC, three-phase AC circuit formulas. They have to apply to our basis. So this is how we calculate the line current base. That we chose, and I calculate that. This is not the only way to calculate it, but it tends to be an easy one. Well, now what? Well, for a Y-connected impedance, a Y-connected impedance is a relationship between a line to neutral current and a line to neutral voltage and a line current. So if I need a Y-connected impedance base, calculate it. Okay? If it would happen to be a delta-connected impedance and I needed that kind of base, calculate that. Calculate whatever you need using the established three-phase AC circuit relationships like these. And there are lots of others. Okay? But in general, these are the things that we need. Okay? We don't need a whole bunch of other variations. There are some, and one very handy one we'll use quite a bit, but we'll get there in time. All right? So, process is the same. We're gonna pin the tail on the donkey. Somewhere in our circuit, we're gonna pick S3 phase and V line to line bases. Okay? Now, if we need a real power base or reactive power base, check this out. Okay, we've alluded to this, but we haven't really addressed it yet. How do I put this in per unit? This is a complex power, note the little bar. How do I put that per unit? Same way, divided by the base. Well, here is the complex power written in rectangular form. How do I put it in per unit? Divided by the base. Divide this by the base. So look what happens right here. If I plug in the number in complex form, I've got P plus J cubed, both of which are divided by S base. So P in watts is going to get divided by S in volts amperes. Q in bars is going to get divided by S in volts amperes. What? Watts over VA, what's that going to be? This is a power, and this is a power. Power divided by power is units. This is a power. This is a power. Power divided by power is units. Okay? The point here is that the apparent power base, S base, is the same for complex power, or real power, or reactive power. We only have one power base, and it applies to every power quantity. Same kind of thing happens to impedance. Okay? I could talk about a complex impedance right here. Z. R plus JX. Z complex divided by Z base. R, X, and Z. Okay? So we don't talk about an R base. We don't talk about an X base. We just have Z base. We don't talk about a P base. We don't talk about a Q base. We just talk about S base. Okay? All right, so make sure you keep up with that. Okay? Now, this right here is one of the little formulas that we use all the time. Okay? This one right here in particular. Most of the time, what we need in power engineering applications is we need a power base, we need a voltage base, and we need an impedance base. We usually don't need current base. Okay? Sometimes we do, but usually not. I want that impedance base, and I want it bad. And I want it fast. I want it yesterday. So what's the best way to get it? Well, the best way to get it, best way to get that is to avoid this little sequence, okay? Remember, I'm going to pick these two. Once I pick these two, I can calculate a line of neutral voltage base, then I can calculate a line current base, then I can calculate an impedance base. That's 1, 2, 3 calculations. I need to be faster than that. Okay,
here's the calculation for the line current base. These two I chose, right? So I've got these two. Bam, calculate that. Now what? Well, now I could calculate the line neutral voltage base. There it is. And then I can plug in my result for the line current base. Now, if you substitute this right here and do this algebra, the formula for Z base comes out this way. And notice why this is handy. I want that and I want it yesterday. These are the two things I chose. All right, so I can calculate this in one step. I don't have to do 1, 2, 3 steps, okay? So this little formula right here, we use this all the time. It allows us to calculate the impedance base that we want in one step, based on the two things that we normally pick. Okay? Now, just like we've talked about, once I pick bases and calculate others that I need, once I do that in any circuit, the bases are the same everywhere until I move across the transformer in the circuit. When I move across the transformer in the circuit, the voltage base changes. And as soon as that happens, then all the other bases change as well, except power. Okay? Now, this is one of those little formulas right here that my guess is before we're done taking tests in this class, my guess is half of you will somehow foul that up. How could that be? It looks so simple. It is. Okay? But that little formula applies only in three-phase applications. Okay? And sometimes you will try to apply that formula, and it's a single-phase problem that I'm giving you to work. Sometimes you will apply that little formula, and you will forget that it's the line-to-line voltage base in the numerator. Sometimes you will apply that formula, and you will forget that it is three-phase power in the denominator. Okay? With all this line-to-line, line-to-neutral, single-phase, three-phase, all that gets jumbled up in your little brains. I don't mean that in an insulting way at all. Okay? Things get jumbled up. It's a lot of stuff to keep up with, especially under pressure. All right? So if in doubt, that always works. Okay? You can follow along each step, each variable, each quantity, and you won't ever inadvertently plug in the wrong things right here. It's easy to do. It doesn't look like it, but again, half of you will do that before we're done. Okay? I mean, it just happens. Okay? It just happens. These are just some other variations. I think we've talked about most of this stuff. All right, there's our same little formula. Okay? Now, here's a way that you can get hosed up. One way, this is what I just showed you, a variation on that is right here. Okay? But notice that this version of the formula has line to neutral voltage squared and single phase power in the denominator. If you do per unit correctly, this and this will give you the same number. But if you get this numerator and that denominator, or any combination of those other than the one shown, you're not going to get the same number. Okay? It's easy to get this fouled up. Much easier than you think. Okay? Of course, if we want to talk about a single phase power base, and sometimes we do, well, we have to remember that three-phase power is simply 3 times the one-phase power. We already mentioned that S base, P base, and Q base, those are all the same. Same thing is true for impedance. Z base is equal to R base and X base. All those are the same. All right, I mentioned about delta connected impedances.
We know that for balanced connections of impedances, that Z delta is equal to 3ZY. This is the one we use most. Occasionally, though, we need that. Okay? So there's lots of these kinds of little formulas. But the main line thing that we need, and what we do, is we pick those two and we calculate that. We do that over. Okay? Occasionally, we need some of those little variations. And we'll just kind of wade into them and learn how to do this. You might say by example, we'll start that next time. Any questions about this? Thank you. All right, we're done. Go home.